Hi everyone. Today we are going to be jumping into a plugin called Horster, which is one of the stranger plugins, at least as far as the name is concerned. It's apparently a combination of a horse and a rooster, because everything in Grasshopper needs to be named after an animal. I have no idea how they came up with the name, but basically what it allows us to do is to get information about the camera in Rhino, and with that, it becomes a really useful tool for annotating or building up dashboards, or if you are trying to do like an urban scale analysis and you need to move along a street and you need the camera to, follow your analysis points, things like that. So it's pretty great. So this first version here, this tutorial is going to deal with the top half of this definition, which we've given you to follow along with. And the next tutorial will be a little bit more advanced. We'll deal with those two down there. So this first bit, all we're trying to do is get some little dots here, which could represent just about anything. They could be, points on top of the buildings that you're analyzing in a complicated urban scenario. They could be anything, it doesn't matter. But what we're going to try and do is set it up so that they will always face the camera. And you could use this to do it once in case you have a still animation where your building is not moving, but maybe you're iterating through different options. Or you could have it so that it follows the camera if the camera is moving. Like let's say you are panning across Manhattan and analyzing multiple sites as part of your animation. You could have those objects constantly orienting towards the camera. So first things first, there's a little bit of, again, sort of arbitrary geometry we've created just for the purpose of this tutorial. But we've used, this is, again, Horster is the only plugin you need for this this tutorial. This is all base Grasshopper down here. We've just made a sort of random population of points here. So this controls the number of points. We are going to move them up in space like that. And so we've just created a random distribution of heights. So to do that, the random component, which we typically argue against using because there's, again, it's random. The whole point of this course is analysis, but here it's perfectly fine. So you construct a domain of the heights, so in this case 0 to 10, and a number of heights, which in this case we're just pulling. We're going to make an equal number of random heights based on the length of the list here, and we've moved them in space. So once we have those, we are going to orient this circle to them. And so this is just a circle that we've drawn here with a radius. And we are using this orient direction component, which is fantastic because what it does is it lets you take this geometry and starting at a base point, which in this case is the origin, because that's the same point we've used to create this circle. And you can orient it to a target point, which is all of our points floating in space. But then you can also specify a direction. And by default, the direction, well, we've defined it here as a unit z-vector, so pointing straight up. And what we're going to do is create a target vector based on the direction of the camera. Now, one thing that I want to point out that's very important, the scale, the overall length of the vector is very important. So we're using a unit z-vector, which means the total length is 1. And you'll see, we'll get to this part in a moment, but it's very important that we use a unit z-vector as well. If the vectors are different lengths, Orient will try and scale the geometry to accommodate the difference in those vectors. So always use unit vectors when you're using this orient direction component. But what that's going to allow us to do is we can orient these points into space. But right now they're just facing in one direction, and we want them to track the camera. So in Horster, here, there is a component get camera, which is right here. There's basically get camera and set camera are the two components we're going to be using. There's a few others, animate, and I don't really even know what these do. I don't ever use them. But basically, when you turn your camera on to true, it will give you the location of the camera, which is a point in space where the camera is currently. It will give you the target, which is where the camera is looking. And we can see that point here. That's what we're looking at. And it will also give you the lens length and the up direction for the camera, which we don't need for this particular tutorial. So if we were to pivot here, we can turn Horster off and then turn it back on, and now it knows that the camera is in a different location. And what we're doing is just creating a 2-point vector from the location to the target. So again, this doesn't update automatically, but anytime we turn Horster on and off, it will figure out that location and that target, draw a vector. We can unitize that vector and just pass that data into our orient direction component. Now, if we want that to keep up with a rotating camera, we can use this timer. And this is sort of a cool component. It doesn't appear to be showing up for some reason, but this is base grasshopper. And if you just type timer and pull it up, it's somewhere. It's probably under utilities. Here it is. Yep, timer. So a timer, you can plug that in to any component, and what it will do, so you just sort of drag from the arrow and click it. So you can turn it, anything, into a sort of automatically updating component. Now, for the most part in Grasshopper, that's not necessary because things are not constantly updating. But in the case of Horster, if we enable this guy, so now this is going to update every 2 seconds. And so if I turn in 2 seconds, it will update that vector. And you can set that interval to be whatever you want. And if you make it 20 milliseconds, it's going to be pretty smooth. It's going to keep that orientation all the time. So if those were little dots, again, for some notation that you're trying to put on top of your animated GIF of your iterative model, that would be a way to do it. So let's turn that off for the moment. And again, so if you turn it on, if you just wanted to do this once, if you're just setting up like a still image, you could do that. You wouldn't need the timer. You could disable that, and that will stay facing the way you want it. Okay, so let's do something a little bit cooler. I'm going to disable this guy. This is the same script, but just a little bit more advanced. So what we've done here is taken those same points, random population of points, moved them up in space, and what we've done is created some spheres instead of two-dimensional circles. And we have colored them so that the ones that are closest to the camera are bright magenta, and then that color sort of falls off. And then we've also scaled them based on that same relationship. And so if we enable them, we can turn it here, and then these will switch like that. And so you can imagine if this was a script where things were moving, I guess it's not that fast, but anything that's animated, if this was a script where your camera were moving, this would be more than fast enough to update for every single frame in the animation. And so it's a cool, it's a cool way to play with the sort of visualization that makes something a little bit more sophisticated than just a standard still image. So the way that we've built this up is we've taken the location from Horster, which again is just a point in space. It's where the camera is. And we've found the distance between that and the points that are the centers for these spheres. And again, we've done two things. We've scaled them and we've colored them. So the coloring is quite simple. We just take those distance values and come over here to the gradient. And at this point, you guys should all be familiar with this gradient component. It just takes the values in to t here as the parameters. And it wants a lower bound and an upper bound. And the easiest way to get that is just to find the bounds here and deconstruct the domain. And again, I mean, these guys are all under math, under domain, bounds, deconstruct domain. What we've done here is I've just flipped this a little bit so that the start of the domain, basically the points that are furthest away are getting the lightest color. So the largest distance is getting the lightest color. The scaling factor is just a little bit more complicated. We're taking the distances and again deconstructing the domain, and we're using this remap component, which is a component that you should definitely know about when you're scaling data. A lot of times in your iterative models, you're going to want to take some information and maintain the relationship and the scale of that information, but you might want to transform it to a different domain. And so what remap does is it takes your values and it takes the original bounds of your values and it just remaps them to a new domain, which you set here. And when you are scaling, so up here, we're going to scale these spheres based on that factor. So we are just creating a domain where the largest spheres will be scaled just 10% larger than they were, and the smallest spheres will be scaled all the way down to about a third of their size. And if we were to increase this, now we'll see that the largest spheres are quite large and the smallest spheres are still fairly small. And so you can do that, whatever makes the most sense for probably not that small, but whatever makes the most sense for your animation and what you're trying to show, this is how you could do that. And so again, we've just scaled the spheres and then oriented them in place. So it's basically the same script, just with a little bit more information taken from that location point. Okay, I think that's it. And in the next tutorial, we'll get into some more advanced stuff with Horster.